Welcome everyone to Haskell Love Conference. This is the Joy Room, and here we are having a keynote from the man who doesn't need to be introduced, Peyton Jones from Microsoft Research Cambridge. He researches the implementations and applications of functional programming languages. He was heavily involved in the design of the Haskell programming language and the development of the Glasgow Haskell Compiler. On a personal note, I want to add that I absolutely love your talks about talks, and I've learned a lot, and they were very, very inspiring for me. So thank you so much. We're excited to have you. Welcome, Simon.
Great, thank you, Ollie. This is exciting. It's great to be among Haskellers. I've been listening to some of your talks. Thank you so much. This talk is about a love story, really, that I've been happy enough to participate in. So it's very suitable for the conference. Please ask questions as we go along, and I'll sort of pause every now and again for Ollie to voice some of them. She's going to sort of collate questions as we go. But I shall chug along. But it'd be more fun for me if you would make comments or ask questions as we go, and I can see the chat going on the side as well. Okay, so what's the world's most widely used purely functional programming language? Well, obviously Haskell, right? So it's there are quite a lot of other functional languages, but they're not really purely functional the same way that Haskell is. So hence the love. But actually, it's not. Really, the world's most widely used purely functional programming language is Excel. Oh, by the way, let me just check, Ollie. Everybody can see the slides changing. Is that right?
Yes.
Yep.
Correct.
Okay. Good. Just checking. So Excel is a functional programming language. There are no side effects when you write Excel formulae, and it's used by, I have to tell you, a lot more people than use Haskell. So it feels like an opportunity. The love story is the opportunity that I found working for Microsoft to try to make some difference to Excel. So one of the things I asked myself was, what would make Excel be a really good functional programming language? Because at the moment, it's really quite a weak one. And there are two fundamental components that would make Excel good. One is the ability to define new functions. Because at the moment, Excel has 600 built-in functions, but you can't define new ones, at least unless you switch language and write in VBA or something, or JavaScript. So it would be great if you could write in Excel's own formula language, new function, just like you can in a normal programming language, so that the language you write in can reflect the computations of you, the domain expert. So I'd like it if any worksheet could become a function, and we'll see that shortly. The second component is, it would be good if the data that your language, in this case Excel, can manipulate, reflects the values of the domain expert. If you're manipulating vectors in three-dimensional space, you want to manipulate vectors. You don't want to manipulate three individual scalars one by one. So we'd like arrays and records and vectors and numbers with units and probability distributions and all of those things, pictures and media, all just to be values that can be manipulated by an Excel formula, just as they can really in a normal programming language. And in particular, one of these values could live in a cell and be the input to or the result from a function. So if we had these two pieces and then they nest so that functions can call functions and data values can contain data values which can contain more data values, then you have a sort of compositional story that we're quite used to for conventional programming that lets you make arbitrarily complex structures by snapping together smaller pieces. So hence the Lego picture here. So this was my sort of aspiration, and I've been talking to the Excel team in Microsoft ever since I started at Microsoft, which is 1998. And they have to say they've been extremely receptive. But Excel is a big, complicated product with a lot of users. It's hard to shift it quickly. But some stuff has begun to happen. Here's an example. I think last year, Microsoft released dynamic arrays for Excel. Here are a few blog posts about dynamic arrays, which means that arrays become much more first-class values without typing Control-Shift-Enter for an array formula. They're just native first-class values now, much better. And then this idea of having records in cells, that's surfaced to something called linked data types, and you can search for that and take a preview of that. It's all connected to much richer data sources. So a cell could contain a city, and you can use record selection to get the population of the city or the picture of the city. It's all so just nested record values. that's in the world of values, and I'm not going to talk much about that today, but in the world of functions, let me go back to functions then. We'd like to make Excel functions reflect the abstractions of end users. And this was a paper that was at ICFP in 2003. Here's the front page, which we described a way to make an Excel worksheet into a function. I'm just going to explain that in a bit more detail because it's the background for this talk. So if you search on any search engine for the word Excel mega formula, you'll find this page is pretty much the first hit. And here's the example it gives. I want to write a formula that takes a URL written at the bottom of the page here and extracts just the bit after the last slash, in this case, tips. And the page goes on to say, look, here's a little spreadsheet with 4 or 5 cells. I've put the formulae in the right-hand column and the values in the left-hand column, so you can see. And it says, you know, I'm not going to go to the details, but it's sort of searching for the slash and indexing into the string and doing that kind of thing. But in the bottom, in cell A6, we end up with the right answer. And then it says, oh, okay, so now glue those 6 formulae together into one formula. That's the mega formula, which I've written at the bottom of the slide here. And you can use that anywhere you want to do this. Just copy paste. Well, then rather hilariously, it goes on to say, I quote, keep in mind that a complex formula such as this is virtually impossible to understand. Therefore, use this type of formula only when you are absolutely certain that it works correctly and you are sure that you will never need to modify it in the future. Hands up, anybody who's written a program that they're absolutely certain that it works correctly and that they are sure that they will never need to modify in the future. Scary. It would be funny if it wasn't so sad. So imagine though, and this is what we presented in the paper, here's a sort of mock-up of what I would love to see in Excel, that you could define a new function just by annotating a worksheet. So here's the very same worksheet that I showed you, right? Except in column B are the computations, and except in this right-hand task pane, I'm just nominating several things. I'm giving a name to the function. Here I've called it url.domain. Up in the returns box at the top, I'm saying this is where the result lands. It lands in cell B16, this is slightly different function, actually gets the domain, not the bit at the end. And then the argument is nominated at the bottom as being in cell B4. And you can nominate as many arguments as you like. So I've just taken an ordinary spreadsheet and I've nominated an output cell and 1 or more input cells. And that turns it into a function that I can call many times. And if I modify this single worksheet, all the calls will get modified. So this is just a mock-up, of course. It's not in Excel at the moment. I would love it to be, and who knows? Eventually it might be. So the key features here are that it's that we're using the very same language. We're not saying switch to VBA or to JavaScript and write your functions. No, you can write functions using ordinary Excel formulae on an ordinary Excel worksheet and then wrap them up as a function that you can call, or maybe group into libraries and export and share. Just what you would expect from functions. Okay, so that's what we would like to see. I would love to see, and I'd even love to see lambda. Just imagine if you could write this in Excel. So Excel does have a thing called SUMIF that adds up all the elements of a vector that satisfies a certain predicate, but the way it expresses the predicate is very weak, right? Imagine you could write lambdas. This would be saying add up all the elements of A1 to A100 for which the element X is either bigger than 100 or smaller than 0. There's no way to do this in Excel, at least not without using auxiliary columns up the wazoo. So I'd love to see Excel really become a functional programming language. So that brings me to the subject of this talk. This is all sort of aspiration, but it's fairly well established. As I say, we wrote the paper some time ago. The subject of this talk really is a way to generalize functions. So let me first identify what the problem is. This is the paper, by the way, which is will be published in Journal of Functional Programming this year, and you can see my co-authors there. And I want to characterize for you first what is the problem that we are trying to solve. Here's a particular example. It's a function called shop that takes, and it's just an ordinary little worksheet at the moment, and it takes the stuff in orange are the inputs. So one orange cell is the tax rate, 20%, and the block of orange cells in F4 through F6, that's the pre-tax prices of the apples, oranges, and bananas that I'm buying. And then this is meant to calculate the total cost, including tax. So I've made a second column, G4 to G6, that contains the tax by multiplying the pre-tax value by the tax. And then I'm adding up that column. So then I add up column F and G to get column H. And then I add up all of column H to get H7, which is the total value. So far, so good. Any worries from anybody? I don't see any questions yet. Please comment or ask questions if anything's obscure. So this is a function I'd like to write, but now the input is a vector of 3 prices in this case. But what if I want to call it like this? I've got a simple snack with 3, let's see, 3 ingredients, crackers, cheese, and juice. I can call that because the function was expecting a vector of 3 elements. But what if I wanted to call it on this pasta with vegetables shopping list, which means I've got to give it a vector of 5 elements? Oh dear, not so good. Not so good, because the function as defined only takes things, you know, it seems to be constrained to just use things of size 3. That would be bad. Okay, so what are we to do? Well, we're functional programmers, right? And the thing that I said for some time was, guys, this isn't so hard. Just use vectors as the input, right? So let's say that the input of pre-tax prices was landed in a single cell, F4, right? That was all 3 elements or all 10 elements. It's just a vector that lands in F4. Then I can compute the tax on the prices in cell G4 by multiplying the vector F4 by the scalar G2. Then I can add up 2 vectors in F4 and G4 to get a vector in H4. And then I can add up the vector in H4 to get a scalar value in H7. I'm hoping that makes sense. Because it's just functional programming over vectors. So what can be so hard? So this is the story that I told. And here's we even wrote a paper, another paper, this is a 2004 paper, about doing this kind of array programming. We tried it out on end users, and sure enough, they managed okay. I think they preferred using element-wise a little bit better. But the trouble is that this way of writing spreadsheets using vectors and arrays as first-class values is not very natural to end users, and it can sometimes be quite hard even for functional programmers. Here is an example. This example computes sort of compound interest on a bank account with some transactions. So here, again, the orange are the inputs and the white cells are computed values. So there's a start date in A3 and a start balance in F3. So I start on the 1st of January 2020 with a balance in my bank account of $100. Then there's a block of transactions which are date amount pairs, right? So that's in A4 through B10. That's the dated transactions. And the goal, and there's also an interest rate in F1 that is the interest rate that I have to pay per day on the outstanding balance. And the goal is to work out at any moment, compute the interest due, add on the transaction, and just keep doing that so you always keep a running balance. Well, it's not too hard to do if you do it element-wise. I've written down the expressions here. I'm not going to go through them. But the point I want to convey here is that there's some, when I'm computing, let's see, C4 through C10, what's that? That column is the number of days since the last transaction. And that's gotten by taking a difference between A3 and A4, and then between A4 and A5, and between A5 and A6. So I've got to compare the A column with itself, but sort of shifted by 1. Then in the columns E and F, where I'm computing the daily balances and the interest on those daily balances, each entry in E depends on the previous entry in F. So the formulae down in the bottom left-hand corner for the E column mentions the F column, and the formulae for the F column mentions the E column. Now, as functional programmers, you say, it's just a scan, you know, of some kind, and you scratch your head a bit, and sure enough, you can write the code. But I hope you can see that it gets harder. So what if we could instead do this solution? This is the subject of my talk. Why don't we instead generalize from an example? So imagine that we wrote shop with 3 elements hard-coded exactly as I did to begin with, and then we somehow automatically generalize it to work for arguments of any size. Let's call that an elastic sheet-defined function. The original sheet-defined function for shop, if I go back 2 slides to here, this is my definition of shop. This is not an elastic sheet-defined function. It only works for things of size 3, exactly 3. But if I go forward again to my generalization slide, I might say maybe I could generalize it to make it elastic somehow. And then there are lots of questions that arise. You know, is there a unique way to do this generalization? Is the generalization predictable enough, or is it just some kind of random best guess? How would we communicate that to the programmer? Would it actually be useful in practice? And so there are plenty of questions like this. Some of them are quite technical. So the idea is, let's take the tools of the programming languages community, that's right, the tools that Haskell programmers know and love, right, and apply them to this technical problem to see if we can make some headway. And that is the subject of this talk. Okay. So, Ollie, any questions so far? I see
no,
comments,
I don't think so.
but not questions.
Yes, there are a lot
what
of
if Excel would
comments.
allow an arbitrary external interpreter? Well, that's a cool idea, but yes, not a subject for this talk. Fine. Okay. So now we get to what we're going to do. Step 1. It's really hard doing anything formal about a grid, right? Because it's kind of like a picture. So let's imagine, and we do this in our heads all the time, let's just imagine writing that grid down in textual form. So on the right-hand side of the slide, I've got the grid, and on the left-hand side of the slide, I've got some text. And it should be pretty obvious. Cell A4 contains 20, cell F5 contains 30, and so forth. G4 to G6, oh, here's the range assignment. So I'm saying that the range G4 to G6 has a single formula. Well, what I really mean is put that formula in the top of a thing in G4 and then copy paste it down. I hope that if you've used spreadsheets, you'll be familiar with this. I've written this out down below the purple box. G4 gets exactly that formula. G5 get that formula adjusted by being moved down 1. So I adjust the F4 to F5, but the dollars mean don't adjust because that's the tax rate, which is in G2, and G6 gets F6. So I can write a range assignment in this textual form. So I only write it once, but it applies to all elements of the range. And the formula I write is for the top left-hand corner of the range. So then H4 to H6, I write a formula, again, exactly the same. This is an element-wise formula again. It's adding up cell F4 with G4, but I copy-paste that down into cell H5 and H6, and which becomes F5 to G5 and so forth. So I hope that this textual translation is pretty straightforward, but it's really helpful being able to see it directly. You can with Excel ask it to display the formulae, but then you lose the values. So in fact, we think it would be quite nice to be able to see the formulas and the values side by side. This is a sort of somewhat orthogonal to the talk, but imagine that you could see the grid view in the left-hand side of the screen, and the calculation view, the textual view, if you like, in the right-hand side of the screen. So the right-hand side here has these range assignments. So now you get these 2 views of the same program, and if you edit in either side, it should be reflected in the other side. It's quite a familiar idea to have 2 views of the same thing. I think this would change the way we think about Excel programming. You could imagine adding commentary and structure to the stuff on the right-hand side as well. It becomes an asset that lets you explain your source code that is usually hidden. So there's a paper about this too, which you'll find in if you search for this title, calculation view, but it's not the subject of this talk. So we tried this out on end users as well, incidentally. Okay, so that was step 1. Let's imagine a textual representation for a sheet full of formulae. Now, step 2 is, if we're going to have these sheet-defined functions, let's wrap them in a function definition. Ollie, yes.
There's one question. Is this implemented, or are these screenshots mockups?
Oh yeah, no, so they're mockups. Actually, I think we have a sort of, Excel is quite extensible. You can do lots of plugins. I believe this calculation view thing, Advait Sarkar, who's a co-author on this, may have a plugin that works with vanilla Excel. I'm not quite sure. So it's more than a mock-up. It actually worked. What I'm not quite completely sure about is whether it worked only because we're inside Microsoft, or whether it's a completely vanilla plugin that anybody else could use. We'll have to ask Advait. If he's listening, he can tell us afterwards. Or maybe type into the chat. Okay, but for now, let's imagine that it's just a mock-up, and what we would love to see. Haha. Now if we're going to have these sheet-defined functions, we need some representation for that, and I'm going to have an explicit function notation. Here's a function definition. I'm going to name the input ranges, here F4 to X6 and G2, and the return says which cell is the return value, and then inside the curly braces, I just have the range assignments for the body of the shop. That is the bit inside the red square. Outside the red square, there might be other formulae, perhaps even in other functions or other parts of the spreadsheet, but this could live within part of a calculation view of a particular worksheet. Okay, so now I've got a way of explicitly describing function definitions. This function definition, though, remember, could also, if you know, previously I gave you a mock-up of a little thing with a side pane that says give a name to the function and nominate the cells. You could imagine all that as a kind of UI that means you don't have to type in text. So that's the two views, the grid view and the calculation view. Fine. Step 3. Okay, so this is the new piece. This is and this is elasticize the function. What we want to do is to really call this function with inputs of various sizes, not just F4 to F7 like we have, F4 to F6 like we have here, but F4 to F6, F4 to F7, F4 to F8, F4 to F9. So in fact, F4 to F3 plus alpha, if alpha is anything bigger than 0. All right, so alpha is going to be the elastic variable. At any call, I'm going to be able to figure out what alpha is. It's implicitly instantiated. So when I call shop at the bottom of the slide on the range K4 to K6, well, that's an input of size 3, so alpha gets to be 3. If I call it on N4 to N9, that's an input of size 6, so alpha gets to be instantiated to 6. And then the idea is that I can call this elastic function instantiating alpha to a different value, and then it'll automatically work for the bigger value because the ranges in the body, G4 to G3 plus alpha, H4 to H3 plus alpha, those ranges expand to match the change in size of the input. Wouldn't that be cool? It would be cool even if you had to write this yourself, but it'd be even cooler if we could figure out, if we could turn the inelastic version to the elastic version. And that's what we're going to do. Okay, so far so good. Alpha equals 0 means empty array. Yes, exactly so. And there may be constraints that mean that your input array can't be empty, and then we'd switch, we'd say 4 plus alpha then. But in general, all of our alphas are always going to be bigger than 0. Yeah, good question. Certainly never negative. Okay, now, there's a little problem with this, which I expected somebody to ask a question about, but hasn't yet. Doesn't that mean, if alpha is big, doesn't that mean that this range H4 to H3 plus alpha, that bumps into H7. Oh, problem, right? 2 definitions for the same cell. Not cool. So we need to figure out what to do about this, and it's really not very hard. What we're going to do is we're going to identify each range assignment as a tile. So each line in the body of the function is a tile. Here I've called them T3, T4, and T5. The input parameters are also tiles, T1 and T2. And those are all the tiles, the input tiles, and 1 for each range assignment. And then in each reference, right, in each range reference, like in that bottom line, H4 to H3 plus alpha, superscript T4, that says this reference is in tile T4. And that means look it up only in tile T4 and not in tile T5. So in effect, both T4 and T5 could have a cell H7, but we know which one to look in. And we can do this annotation based on the original fixed size function, the inelastic function. We do the annotations, and then we keep the tile annotation stable through all the elasticization process. So at this point, you think things are getting a little tricky, right? Do you know you've covered all the bases? Is everything okay? So we turn to the methods of functional programming, and we write a formal semantics. We say, what is a formal semantics? It is a mathematical definition that says, given this text for the function shop, what function does it compute? What, if you give it at any given input, what is the output that it will produce? And we can formally define what that is and be sure that we covered all the bases using our standard tools of functional programming theory, because after all, it now just is a standard functional programming language. It's just a blob of text with concrete syntax and all. Do we need some static analysis? Yes. H7 should be H7 should be H4 plus alpha. No. So going back to this, in cell T5, tile T5, I don't particularly want to change H7 to be H4 plus alpha to get it out of the way. In general, it's very difficult to get everything out of the way of each other. It's easiest just to say there's an H7 in tile T5 and there's an H7 in tile T4, and they don't get mixed up with each other. That's to answer Alex's question. Do we need some static analysis so you can't refer to F5 directly? F5, what's wrong with F5? I don't think I understand that question. You might need to expand a bit. What if you've got a range of references that are defined in several tiles? So the starting point, before elasticization, when I'm at this point, when it's in this inelastic form, that is actually when I'm going to do the tile annotation. And in this form, every cell must be defined by at most one tile. Okay, then I add the tile annotations, and then I elasticize. I did it in the other order in the presentation because I couldn't motivate the tiles until, but in fact, we go fixed size thing, decorate with tiles, elasticize. So, and part of the fixed size thing is no definition for the same cell twice.
One more question. So these references would be some sort of local types?
The reference is some kind of local what?
Local types.
Local types. I don't know what that means. No, I don't think I can answer the question because I don't understand it well enough. If you see anything from Matt McCutcheon on this chat, that is Matthew, who is the primary author of this paper. He really knows what he's talking about. So pay attention to what he says. Okay, how are we doing for time? Yes, I should go on, I think. Right. I want to say a little bit about generalization, which is the key technical insight of the paper, and I'd really like to give you a gut feel for what we do. The goal is figure out where the alphas should be, right? Elasticize the function starting from that single example, the single shop example with no alphas anywhere, and generate the version with the alphas somehow in a unique, most general way. So what do I mean by that? Let's take an analogy with types. Here's function reverse. It has lots of types. It takes a list of ints to a list of ints. Reverse takes a list of bool to a list of bool. It takes a list of pairs of int bool to a list of int bool pairs. And so, in fact, it takes a list of any type to a list of the same type. And so its most general type is, for all A, list of A to list of A. So the idea of polymorphic types is, when a function has many types, see if you can find a unique, most general, often called principal type, and each of the other types is a substitution instance of the most general principal type. Okay, so all of the types that reverse has are substitution instances, by substituting for A, substitution instances of its most general principal type. And this has proved to be extremely powerful as a way of thinking about generalization in the world of types. In fact, I think you all understand this, not quite from birth, but if you've been using Haskell for more than about 10 minutes, you understand this in your guts. And that is what we are going to do with our sheet-defined functions. We want to find a generalization, right, with some free alphas in it, just like in reverse, the type A, list of A to list of A had some free A's, a type variable. Here we're going to have a sort of elasticization variable, alpha, and we want to arrange that all the generalizations of shop are substitution instances of that most general principal generalization. That's our goal. That's our goal. Do for generalizing sheet-defined functions exactly what we do for generalizing types, but amazingly, do it based on a single instance, the thing on the left. Okay, so here's a little picture then. If you imagine all possible generalizations of a function, so on the left here is the original inelastic function, and the blue ovals are meant to be possible generalizations, possible elasticizations with alphas scattered about with them, who knows where. And the green arrows are meant to be is more general than, or going the other way, is a substitution instance of. So the idea is all of these G things are going to be more general than F. They can all be instantiated to get F. But G3 is more general than G2. That is, you can substitute in G3 to get G2. You can substitute in G3 to get G6 and G5. But G3 and G4 are incomparable. Neither is more general than the other. Neither is a substitution instance of the other. That's not good, right? What we would like to have is this. We'd like to exclude the ones. We'd somehow like to pick a subset of the possible generalizations. Let's call them the regular generalizations, a subset of the possible generalizations, in such a way that there is a unique most general one. Okay. If we can do that, if we can identify the regular generalizations in some way, I'm going to elaborate a little bit, then and we can and then among the remainder we can find a unique most general. Then we can have a principal regular generalization, and that is what we want. G3 is the unique most general answer that we seek. So all of the subtlety really rests in how do we decide what regular means? What are good generalizations and what are bad ones? And I want to give you some quick gut feel for what the problems might be and how we might solve them. Here is one. Here is a funny function that takes two input ranges, A1 to A3 and A5 to A7, and returns a single cell that's the sum of A9 to A11, but A9 to A11 is just 1 everywhere. So each of these ranges has size 3, but there's no other connection between them. It's a pretty silly function. So how should we elasticize this? There just aren't enough constraints here to tell us. So here are some possible elasticizations. We could choose to elasticize the first parameter, first argument, A1 to A alpha here, and leave the A5 to A7 alone. Or we could choose to elasticize both of the parameters. That's the second one. Or going downwards, we could elasticize both of the parameters and this A9 to A8 plus gamma thing. Which should we choose? Well, the trouble is that these are not, this is an example of where these different generalizations, they are all generalizations of the very same inelastic function. They can all be specialized to the inelastic function, but they are not comparable with each other. It's an example of, where are we? G1 versus G3. They're not comparable with each other. There is no arrow between them. We don't like that because that's not going to give us, and you can see there's something arbitrary about this anyway. So it's not just a technical point, it's that it's genuinely arbitrary. So what do we do? We simply choose the choice B here. That is, we generalize on the arguments, but we don't couple them because there's no reason to connect the two arguments together. They're not added up to each other, for example. And for the result, since if we had a gamma thing, there'd be no way to fix gamma from the call parameters. So we choose not to elasticize this gamma thing. So we choose B. And we say, but with the way that when I say we choose B, we simply say that A and C are not valid. They're not regular generalizations. So it all focuses on the definition of what regular is. Okay. Second thing. What about size 1 axes? Now here's an example that's easy, right? If I have a function that's here, I'm computing just I'm going to count up the number of non-blank elements of the vector A1 to A10. That's what count does. It counts non-blank elements, I think, and then multiply that by 2 and return it. So it seems obvious how to elasticize that. We just like to say it can take an input of various sizes. But what if it was like this? That I gave a funny function that only took a single cell, A1, as its input. Well, you could still elasticize that, couldn't you? Say A1, isn't that a kind of degenerate range? Maybe we should elasticize that too. But then you'd actually get different answers than if you didn't. There's more than one way to do it. So in fact, what we choose to do is to exclude both B and C and return A. That is, we say B and C are not valid elasticizations, generalizations of, not regular generalizations of A at all. We exclude them. So we don't generalize size 1 at all. Only size 2 or more we regard as being an axis that's a subject of generalization. Finally, there's a matter of what we might call patterns of computation. Now here's the concrete function f takes a function that really just returns its input. It's not its input of size 9, right? It just has a vector b1 to b9, which it copies a into. Remember, copy paste will change that into b2 is a2, b3 is a3, and so forth. Now, we could imagine various elasticizations of that. For example, you could imagine that the function was elasticized so that it returned the first 9 elements of an input vector of arbitrary size. That's choice B. Or choice C here, return the last 9 elements of an input of arbitrary size. Or choice A is return all the elements of the input vector, whatever size it is. And again, these are incomparable generalizations. So again, our choices that we're going to choose to stick with A, and we're going to find a way to say that B and C are not regular generalizations. So I hope I've said enough to convince you that it's not entirely straightforward to say what we mean by a regular generalization, to say there are design choices here, right? So we have to be very careful how we define regular to pick out a well-behaved set, and also a well-behaved set that obeys common sense rules. I've been trying to, in these examples, I've been trying to say it's common sense that if they're coupled together, I add 2 vectors of the same length, then if one grows, the other should grow. That's common sense, isn't it? So we want our regularity definition to reflect common sense. So we, yeah, oh good.
Does it mean that function f a1 returns b, where b equals 2 multiply a1, would not be elasticized until the user elasticizes to a2? And
yes, it means exactly that. Yes, because a1 is of size is of size 1 in both directions, actually, horizontally and vertically. We don't elasticize it. Yes. So if you want to elasticize it so this function will take a vector of arbitrary size, then indeed you must give it a vector of at least size 2 as its input. And in fact, so in fact, if you want it to elasticize both horizontally and vertically, everything in the paper applies both horizontally and vertically. You give it a 2 by 2 or 3 by 3 or 3 by 2, anything that is not 1 in the directions you want to elasticize will elasticize. And if it's 1 in a particular dimension, it won't elasticize that. So would writing b1 colon b1 work? Would you need to go to b1 colon b2? That's a good question, Ed. If you think about making arrays into first-class values in Excel, I think we probably do want to have a distinction between a 1-by-1 array whose only element is 3 and the scalar value 3. So if we had that, then yes, b1 colon b1 would probably work. But that sort of opens another can of worms. Elasticize is trying to convert all fixed array dimensions to a function of unspecified generic dimensions. Yes, exactly so. That is what elasticization, that's what this whole talk is about. How do we generalize from a simple example a function over arrays of fixed size to a function over arrays of general size? And yes, in principle, you could imagine that applying that to other programming languages. But in other programming languages, it's often easier to if you've got an array of unknown size, you tend to write array programming. Excel has this strong predilection towards element-wise programming. But yeah, you could apply it to other things. Okay, now, so much of the subtlety is to do with defining what regular is. And then once we got that, then it's not too hard, it turns out, to write an algorithm that generalizes the function in lots of directions, then with adding lots of unknown variables, lots of alphas, as it were, and then generates lots of constraints for how these alphas must be connected, and then solves those constraints and finds the principal solution. This is all very familiar to people who build type inference engines. We generate constraints and we solve and we write the most general solution. And that will find the principal regular generalization. And along with that, we have a proof. Well, more specifically, Matt McCutcheon on this chat thing has a proof, developed a proof that this really does produce a principal generalization, which gives us some confidence that it's not ad hoc and will produce good answers. Now, before I run out of time, I just want to say one more thing. Because this is a spreadsheet, we're working with people who are interested in, with researchers who are interested in end users. And unlike programming language geeks, they are used to trying things out on the people for whom they are intended. It's a tragic shortcoming of the programming languages community that we do so little in the way of user studies. But here, my colleagues actually did Judith and Advait did a user study on this, and here were their questions, right? So what they did is they tried showing these end users both elastic sheet defined functions and the array programming version, what I showed you as solution 1, and they tried to get them to do the same problem in both ways and asked them which they preferred. And sometimes they asked them to use sheet-defined functions first and then arrays first, and the other time they asked a different batch to do arrays first and then sheet-defined functions first. And then here are the questions that they asked. So it was a smallish study, 20 participants. Was actually, in user studies, that's not ridiculously small because user studies are ridiculously expensive. They showed them a 10-minute video about, only a 10-minute video, that was all they knew about elastic sheet defined functions. So they had a kind of executable mocked up prototype that worked. And they then gave them 2 hours to do 6 tasks using both methods. So here's what they found. The horizontal axis is just the 2 points. Did they use arrays or did they use elastic sheet defined functions? And the vertical axis is something called the NASA Task Load Index questionnaire, which is a sort of standardized questionnaire that you ask people to say, how difficult did you find this? What was your cognitive load? So in this graph, lower is better. So you can see that the elastic things on the right are lower than the array thing on the left, meaning that our users found that elastic sheet defined functions were easier to grok than the array version. You can see the actual examples that they tried in the paper. Interestingly though, this wasn't, the things were not very strongly correlated with cognitive load wasn't significantly affected by programming expertise. The low expertise programmers on the left and the higher expertise programmers on the right. I thought that was intriguing. I expected that to make a difference. User studies can surprise you. Okay,
there is
so
a kind of philosophical question.
Yes.
Why do you think end user studies are so rare in programming language research?
Why are they so rare? Because they're so difficult, right? If I wanted to say, is my approach to parametric polymorphism, is this a good approach to, I don't know, records or quantified constraints? Are quantified constraints in Haskell a good thing? Then it's quite difficult to find enough users who to test that on, or to set up tests that'll do it. And the kind of people who prove theorems about the soundness of quantified constraints tend to be not the kind of people who are good at doing user studies. We're sort of too siloed. And one of the things I've liked about this project, one of the love aspects of it, is that it's enabled the human experience and design silo to interact with the programming languages silo to the mutual benefit of both. I'd love to see more of that happen. So here it is. Yes, I'm gonna wrap up so that anybody can ask more questions. As you'll see when you read the paper, it's a long paper and it's quite technical. So I really like the way that that we've been able to apply the quite heavy duty tools of the programming languages world to this very end user focused problem to materially, I hope, benefit end users. And my earnest hope is that something like this will end up in a spreadsheet, Excel, or something else. If you're doing the competition, feel free. It's all in the public domain. Just have a go. But I hope I hope we'll see it in practice, because I want to finish with a slightly tongue-in-cheek remark. My working life has been comprised of 3 main components: functional programming, and Haskell in particular; education. Many of you will know that I've been quite involved in education and reforming education for school children, and working for Microsoft for the last 20 years, in particular the stuff with Excel. So my dream is to bring these 3 parts of my life together in one glorious apotheosis, right? To use Excel to teach actual, pure, scalable, composable functional programming to school children. Thanks very much. Let's look and answer any other questions.